Okay, thank you. So first of all, I would like to uh, thank Marias and Miguel and Pedro for inviting me for this wonderful workshop. I'm very happy and enjoying this workshop. So today I would like to talk about some analysis of gravitational waves, taking into account the wave effect as well as a spin effect, because gravitational waves are spin to waves. So, and I'm going to talk about that. So, okay. And this is the fourth day of the workshop, so maybe I do not need much go in detail about the introduction, but we have many black hole and gravitational wave events, and we are living with the era of the gravitational wave astronomy. And future, we maybe even accessible to even more precise sensitivity, accuracy, and maybe we accessible to the many events related to the cosmology, the supermassive black holes, and massive black holes. And these are will be observed by partial timing array and space-based interferometers and ground-based interferometers. So this is multi-messenger gravitational wave astronomy. Especially these regions, uh, if we understand the physics of the gravitational waves of these regions, then we can understand the matter distribution of these supermassive black holes or galaxy scales. So it's very interesting to understand the nature of the gravitational waves, and especially wave nature and nature. So let's consider this kind of setup. So suppose there are some source gravitational waves, for example, generated by binary gravitational waves coming in this direction and lensed by this lens black hole, rotating or non-rotating, or supermassive or more compact. In any case, after lensing, we observe the gravitational waves here. Okay, so if the wavelength is very short, then we can use the geometrical optics limit. So in this limit, we analyze the propagation of the gravitational waves by using the geodesic equation, and basically we are focusing on the propagation of the gravitational waves along the rays, so geodesic. Okay, and even introduce the correction for the this disorder, inverse of the frequency. And it is already nicely covered by the Jose Maria's talk and his talk, and we will be able to see it in this amplification or time delay or phase shift of the gravitational waves. And these are the important observable quantities, this geometric optics limit. And then if we also take into account the spin of the gravitational waves, then we can also see some interesting phenomena like gravitational Faraday rotation or gravitational spin Hall effect investigating in these papers. So this means that this suppose this schematically this is a polarization direction, okay? And then during the propagation, during the curved space-time, the polarization direction is will be rotated and then observed by us. So this can be analyzed by this geodesic equation with some correction by spin effects, and several approaches are proposed, and this field is also very actively explored recently. Especially, so this is this plot is I took this plot with Marius and Miguel's papers, and so this x-axis is wavelength. So if you go to the longer wavelength, then this difference of the arrival proper time of the signal is increasing. So this is the difference between light polarization and left-hand polarization. This is gravitational spin Hall effect to a non-GSHE geodesic case. So this difference is growing and growing for longer wavelengths. So it's natural to expect that this continues, but maybe not diverging. So if we can consider this kind of quantities in wave optics analysis, I think that's very interesting. Okay, so wave optics can deal with the gravitational waves have longer, which has a longer wavelengths, even comparable or longer than the typical scale of the lens objects. Okay. So in this case, in addition to this amplification time general phase shift, we expect that interference between, okay, for example, in this direct ray or winding ray, meaning that the direct ray coming from the source and observer, and winding ray means that actually going this way and winding around the black hole, and then going to observer. So such kind of interference or diffraction and superradiance, which was already nicely covered by Richard's talk. So this kind of interesting phenomena can be expected in the wave optics. And neglecting the spin of the gravitational waves, we can deal with wave optics by using scalar wave equation. Okay. So scalar wave optics, there are several approaches because so solving this a scalar wave equation numerically is a very highly computationally cost. So there are, of course, you can directly solve, but there are several approaches. This perturbative approaches is one of them. So let me briefly explain that. So in this case, we assume that the curvature of the spacetime is very small, and this scalar field propagating on such a background. And this is a wave equation for scalar field. And then we consider this is a Newton potential expressing the curvature of the spacetime. Okay. Then we can define so-called amplification factor ratio between the scalar field and unlensed scalar field. And then if we expand, we can solve this equation by using Green function technique and iteratively obtain the solution by in terms of the series expansion of the small quantity phi. So so long as we are assuming phi is small, okay. And if we parameterize the amplification in this way, so this K and S can be expanded in a series of the in terms of phi, in the power of phi. Okay. Then the first order is a so-called Born approximation investigated in this paper. Takahashi is pioneering paper. Okay. And this variance of these quantities is related to this matter power spectrum. So it's actually given by the integral of a matter power spectrum. So it's not that simple, but important thing is that this is directly related to the matter distribution of the lens or the space-time around lens black hole. So in principle, we can decipher or at least, okay, information of the matter distribution is encoded in the amplification factor. And recently, this result is generalized up to second order and third order of the Newton potential. And these terms are typically smaller than the Born approximation. So that fact is confirmed by this Mizuno and Suyama paper recently. And a quantum scattering technique by Jiria's talk and numerical calculations are also Excel's talk introduced such a technique. And this Anderson's review paper is, I think, also very useful. And this number and the collaborators' work is, I think, very interesting. So let me introduce one of them. So this is one of this number and collaborators' paper where they investigate this scalar wave propagation of the um, assuming the existence of a black hole lens. So when this left-hand side is a longer wavelength case, and the right-hand side, this one is the shorter wavelength case. So more like geometrical optics limit. So you see, this is very strong, this direction. So this will be acoustics in geometrical optics limit. But in wave optics case, that it is not that strong. Okay, that kind of difference occurs in between the geometrical optics and the wave optics. Okay, then finally, we would like to take into account this spin of the gravitational waves, because gravitational waves have a spin-to nature, so it would be, I think, interesting if we can take into account this spin effect or polarization of gravitational waves directly by solving this Chukovsky equation. Let me briefly give you some insight of this Chukovsky formalism. So Chukovsky formalism is based on this Newman-Penrose or Gerows-Held Penrose formalism, and to isolate the gravitational wave perturbation and variable and identify some master variable that is governing the evolution of all the metric perturbation. And at the end of the day, you can obtain this PDE for linear perturbations on rotating black hole spacetime. And this master variable is called psi4. It's Weyl scalar. It is separable into angular part and radial part. Radial part is this R, and angular part is this S. And it is related to this strain of the gravitational waves in this way. So it's the second derivative of strain if you take a far region limit. Okay, so strictly speaking, we are interested in this strain. But in this talk, I mainly focus on this psi4. And you can convert this psi4 to this strain by multiplying some inverse operator, which is known. Okay, and this angular part is given by so-called spin-weighted spheroidal harmonics, which is generalization of spherical harmonics. Because we are now considering rotating black hole, so there is no spherical symmetry, but axis symmetry. So this spheroidal harmonics is axis symmetric case. Okay, then the radial part is given by solving this inhomogeneous equation. This is sometimes called radial Chukovsky equation. So I do not give a detailed definition of this k or lambda or etc. something. But it's not important in this talk, so you can forget about these details. But I just would like to give you some insight. Okay, so this sum operator and radial function and this source term. So how to solve this? Okay, we now following the green function technique, and we would like to have a two independent solution of the inhomogeneous equation. Homogeneous equation. Okay, so homogeneous equation, the useful choice of the independent two solutions is some up and in solutions. And up solution is a solution of the homogeneous equation satisfying this boundary condition, namely the outgoing boundary condition at the infinity. On the other hand, this in solution satisfies this ingoing boundary condition at event horizon. Okay, these are the clearly two independent solution unless this omega is QNM frequency. Okay, so these are the two independent solutions, and by using them, we can construct green function. Then using this green function G and integrate with the source term, we obtain the solution for the inhomogeneous equation. So, okay, then how to obtain this up and in solution? So one way is use the exact solution, which is already very much in detail introduced by Felix's talk. So this is very useful, but it works only for asymptotically de Sitter case. It's a caveat, okay? But so long as it's space-time is asymptotically de Sitter or anti-de Sitter, strictly speaking, ADS 5, in that case, we can formulate the QNMs or wave scattering in an exact manner. Okay, so I'm not explaining these formulas in detail, but in any case, so it's written exactly. So QNMs is given by this kind of simple relation. So Wronskian between two independent up and in solution, the vanishing, and the angular part is also vanishing. And gray body factor or reflection rate or absorption rate can be written down in this way as well. So, and this green function can be written down in this way by using this in and up solution composed from the Hoyne function, general Hoyne function. So all of them we formulated in this paper. Okay. QNM is formulated by previously in the Hatsuda's paper. Okay, so this is a case of the scalar field scattering, but formalism works for any spin. This result is a scalar field. Okay, the y-axis is the green function squared, and the x-axis is our frequency. So we see the small modulations, and when you go to high frequency, it seems like diverging, but it suggests that caustics, okay, which we see in the previous slide. And this scale is related to this unstable circular orbit. And also, it's already covered by Felix's talk, so it's very nice to have this black hole image by using these techniques. Okay, and so yeah, there are some caveats for extrapolation, but maybe I can skip and yeah, if some of you are interested in, maybe I can come back to this point. So how to extrapolate? Okay, and beyond this kind of formula, this exact solution seems to be very useful to see some relation between particle physics and the Q-Quesadenomer mode frequencies, which I do not actually, I am not that familiar with. But recently, this conformal field theory technique, using conformal field theory technique, some correspondence known as some Carl CFT correspondence or QNM Seiberg-Witten correspondence or something has been very, very actively investigated. And some of the paper even claim that the connection coefficients of the Hoyne function is clarified in terms of Nekrasov function. But yeah, it seems much more complicated, but exact solution seems to be very helpful to clarify some symmetry or structure of the equations. I'm very interested in that field too. Okay, then finally, I'd like to introduce this paper, our paper of numerical calculation. And this corresponding author is this Keiichiro Kubota. He is a PhD student in YITP, Yukawa Institute in Kyoto University. And he is a corresponding author and did everything, but unfortunately he cannot make it to attend this conference. So yeah, I would like to introduce the result obtained by Keiichiro. And he is finishing PhD next year and now in the job market. Okay, this conversion check, maybe I can skip this. Okay, so the situation we consider is expressed by this movie. So this is a source we assume, which is a stationary black hole binary. Okay, and in this direction, you have a linear polarization called plus mode. Okay, and in this z plus z direction, you obtain this right-handed circular polarization. And the minus z direction, you have the left-handed circular polarization. So these are the very peculiar behavior of this spin-2 waves. Okay, so we are mostly interested in the difference of these right and left-handed polarizations. So we try to highlight the difference by investigating these two cases. So this co-rotating case, where the rotation direction of the binary and lens car black hole are the same. And the counter-rotating case, where this rotation direction of this lens car black hole is opposite. Okay, so this is source and gravitational waves and lensed by this black hole, then it's observed. Okay, this is a situation. So, and this is the result. This is a co-rotating case and counter-rotating case. So actually, so this is, it's hard to see the difference in this case. And this is a frequency of 0.5. 0.4, the left panel exhibits this superradiance clearly. But this right panel does not satisfy this condition, so superradiance does not occur. But in left panel, superradiance causes this back scattering. So this source is in this direction, and this is a lens black hole. Okay. And this is a spin dependence. So this is this amplification factor. We define amplification factor by using this psi4 ratio between psi4 and plus unlensed psi4. And this is S equals 0, this blue one, and the orange one is gravitational waves. So scalar field and gravitational waves. So we can see small changes. And we also plotted some analytic formula obtained by geometrical optics, but we are still not clear why this offset occurs. Maybe some factor difference is omitted here, I guess. In any case, okay. So on the other hand, this is a co-rotating and counter-rotating comparison. Okay, we have different beating pattern. And such patterns are also dependent on the rotation parameter of the lens black hole. And if you zoom in, you can see this red line is the highest deviation, has highest deviation. Okay. So these large differences in extremal case, so there plus extremal case, I would say. So in this case is related to actually the fact that the Quezon amount of frequency is accumulating in this limit. Okay. Because this source gravitational waves excite this Quezon number mode of the lens black hole, and then that excited Quezon number mode imprinted actually in principle to the lens gravitational waves. So I think there is a very important relation between the lensing of the gravitational waves and the Quezon modes. Okay, so let me briefly introduce some Quezon modes. So this is much more related to black hole spectroscopy. So previously I introduced the green function technique, how to solve the Chukovsky equation. So if you continue that process for bring down gravitational waves, you can perform the integral of the green function and source term, and by separating out that in the source dependent term and the source independent term. So this omega is QNM, and B is the so-called excitation factor, and this I is the source dependent term. And this omega and B does not depend on source and depends only on mass and spin of the remnant black hole. So in the context of ring down. But in this context, this lensed black hole. Okay, so this is the QNM frequency of the 2-2 modes. So this is the imaginary part, and this is the real part. And most quasi normal modes goes to this point, and so it means longer lived modes. So that's why I think the deviation in the lens gravitational waves is larger for this limit. But you notice that this fifth overtone is some strange behavior. Right? Only this one does not go to this point. And actually, this was found almost 30 years ago, and it has been long-standing mystery. And recently, I noticed that this one can be interpreted as avoided crossing, so-called avoided crossing, which has been known in the field of the quantum mechanics. And further, during this avoided crossing, this excitation factor is very much amplified. So I think this resonance phenomena might be encoded in the lensed gravitational waves. So it would be, I think, interesting to explore the relation between this resonance and lensed gravitational waves. Okay, and this is a higher multiple case, so it's even sharper resonance occurs. Okay, so this is a summary. So we are interested in the spin effect and the wave effect in the gravitational waves because they are the nature of gravitational waves, and they would provide the information for matter density distributions and the lens black hole and quasi-normal modes. But formulation is, there are several formulations, but mostly more computational cost are required for the calculation of the longer wavelength case. So still, it's just a first step, and our result is still not directly connected to observable. So it's still important to continue this direction with various approaches and considering the possibilities of applications or observables too. Okay, thank you.